Welcome back, students, to Chem 101. My name is Professor El Hawari, and today we will be going over Chapter 12. Chapter 12 is called Energy, Power, and Climate Change. We'll be going over the 21st Century textbook by Kimberly Waldron. And again, for every chapter, we have an opener. So this chapter opener starts on page 345 and it reads: The Simon Langton Grammar School for Boys sits in the countryside near the medieval town of Canterbury, England. In many ways, it's just like other private schools in Great Britain. What sets it apart is one particular hallway, the most heavily trod on the whole campus. In that hallway, the lighting is not connected to the electrical grid. Instead, it's connected to unique floor tiles that pepper the hallway from end to end. These revolutionary tiles use the energy from student footfalls to power the hallway lights as well as small lights in the tiles that are illuminated when someone steps on them. These tiles are the brainchild of Lawrence Kimball Cook, a 20 something British inventor and designer who founded the company Pavilion Systems that sells the tiles. When a foot strikes a Pavilion tile, the tile depresses about 5 millimeters, a distance barely discernible to the walker. The friction generated by this tiny movement is converted to electricity, a flow of electrons, by a still secret method that Pavilion Systems has not revealed. About 5% of the energy generated from footfalls goes to lightening the tile itself, and the rest can be stored in a battery or used for anything that requires electricity. The tiles are earth friendly and practical in other ways. They're made from recycled rubber and can be used outdoors in any weather. Pavilion Systems may have a patent on its own floor tiles, but it does not have a monopoly on this groundbreaking idea. A company in the Netherlands, InView, has developed a spring-loaded dance floor that converts dance into power. Nightclubs with bone-jarring speakers and dazzling light shows are notorious power hogs, but this new technology will eventually allow dance power to offset some, perhaps all, of the power usage at nightclubs. One goal of this chapter is to discuss exciting, original sources of energy like this one. We look at several examples of new ways to store energy and generate power. But first, we'll talk about the terms energy and power to get a deeper understanding of what they are and how they differ. We'll also consider the predominant source of energy that we now use, fossil fuels, and see why it's imperative that we start to focus on other sources. Finally, we'll turn our attention to new energy ideas, especially those that tap our most underutilized energy resource, the sun. So, as chapter 12 tells us in the introduction, the floor tiles and dance floors are being creatively altered to produce electricity. There are many original and exciting new ways to produce energy that may help to reduce our dependence on fossil fuels. And again, that's the main reason why we have global warming. Energy, the definition of it is that it's the ability to apply a force over distance, which is also a definition shared in physics. As you can see, when water moves over a water wheel, it provides a force to turn the wheel, and this movement generates a lot of energy. So, as you can see in the picture here, and this is a way to generate energy for this little house. Now, energy could be transferred from one form to another, which is called the conservation of energy. So, as you can see here, nuclear power plants, the energy generated there would be converted to electricity, electrical energy, and then this electrical energy is used by the blender to make your smoothie. Now, the protein smooth, this is you got chemical energy that's inside food. Now, the person eats it, the person uses that chemical energy and converts it to mechanical energy by lifting up the boxes. Now, when the car moves down the road, it will convert the chemical energy into mechanical energy, moving energy. and then it gets the energy from the fuel source, in this case, the diesel. So, as you can see, the energy cycle energy is not created or destroyed, is converted from one form to the next. Power, as a definition, is the amount of energy generated or used in a certain amount of time. So, and that gives rise to the definition of the watt. You might have heard of it if you're purchasing a light bulb, the wattage. So, a watt is the number of joules of energy transferred per second. So, joules is a unit of energy. So, when you divide energy by time, you get your power. So, a 100-watt light bulb uses 100 joules of energy per second. As you see here, this wheel rotates at a rate of 100 rates per minute, while this rotates at a rate of 10 rates per minute. So, as you can see, this wheel is much, much more powerful because it's using a lot of power. So, 100 rates per minute has a lot more power than a wheel turning at 10 RPMs. Now, let's talk about the first law of thermodynamics, which states that the energy cannot be created or destroyed. This is the conservation of energy. Energy could be transferred from one form to another, but you cannot destroy it. All of the energy going into this light bulb is going to be converted to another form of energy. So, electricity goes into the light bulb. Obviously, it will generate light, so this will produce light energy, but it will also heat up, so that will release some thermal energy. Now, if you can see, for an incandescent light bulbs, 2% of the energy is converted to light, and the rest is lost to heat, which is a major problem. And that's why the incandescent light bulb has so many issues, because most of the energy is lost. It's not converted to light, which is not useful if you're trying to turn on the light. Now, let's talk about fossil fuels, what they are, and where we get them. So, as you can see here in the 1970s, which is right here in our graph, and in the 1800s, the main source of energy in the US was wood. So many people, if they want to use energy, they are going to start burning wood, and that's how they got most of their energy. Now, if we turn to the 1900s, you see with the Industrial Revolution, coal was the dominant energy source in the 1900s, as you can see. And then eventually, right here around the 1950s, we see petroleum is the main dominant energy source. So, as you can see, over time, when we discover new technologies and new ways of living, we start relying on different forms of energy. Now, since the 1950s, petroleum, natural gas, and coal have been our primary energy sources. Now, these are all fossil fuels. Now, fossil fuels are derived from organic matter. The organic matter is going to decay, break down over many, 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 many years, and this breakdown is going to create a mixture of carbon based molecules in the ground. Now, once these carbon molecules are extracted, you can get a ton of energy out of them. Now, let's talk about hydrocarbons. It's in the name, hydrocarbons. These are compounds that contain only carbons and hydrogens. For example, CH4, C6H14, C10H22, and so on. These compounds have only carbons and hydrogens. So these are the molecules that are found in fossil fuels. Now, if you start to look at these molecules, they have so many bonds, and that's why you can extract a lot of energy from them, because when you start burning them and breaking down these bonds, you generate a ton of energy. Now, another thing is refineries. Now, these refineries are used to separate fossil fuels into usable fractions. So you get crude oil from the ground, and then you pass it through this machine, this refinery, and this uses now the process of fractional distillation to separate the different liquids based on their boiling point. You can get diesel oil, you get kerosene, you get gasoline, and you heat this fractionating column. So crude oil is a mixture of hydrocarbons that is separated by fractionation. You're going to heat it to a high temperature and then separate it based on mass and other physical properties like boiling point. So it's a very useful equipment. Now, hydrocarbons with the lowest boiling point will travel the furthest up the fractionating column before being recondensed to liquid. So this talks about kind of like distillation. Hydrocarbons with more carbon atoms are heavier, and they have higher boiling points because they have higher surface area and will have more interaction with neighboring molecules. So, this higher temperature is going to be needed to disrupt interactions between these molecules, which makes them boil at a much higher boiling point in the fractionating column. Now, let's talk about fossil fuels and climate change. Fossil fuels release energy when they are combusted, meaning when you burn down these fossil fuels, you're going to get a ton of energy. In order to burn, you need oxygen. So, oxygen is a requirement, it's required for combustion reactions. And when you get gasoline from the ground, it's a mixture of these hydrocarbons. Now, combustion of gasoline, when you burn gasoline, you're going to produce two things: you're going to produce water and you're going to produce carbon dioxide, and very important, you're going to produce a lot of heat. Now, this heat is going to cause the gases to expand, which pushes on the pistons, which turn a crank to turn the axles to make the tires roll. So it's all about gases, gas expansion, and combustion. Now, a car's fuel economy is also related to power. A car that has lots of power can transfer the chemical energy of the fuel into mechanical energy of turning the wheels in a short amount of time. So, power could be expressed in a unit called horsepower, and 1 horsepower is determined to be equal to 746 watts. And fuel economy, now the definition of it is this is the distance a car can travel on a given volume of fuel. Now we have different cars and they have different fuel economies. The textbook gives us a picture of the 2013 Smart Car for Two and the 2013 Dodge Viper SRT 10. As you can see, both of them have very different fuel economies. Now, climate change is a big problem, major issue, because the global temperature is increasing. So, this occurs because the planet is warming at a faster rate than it has in the past. And the reason is because of the presence of carbon dioxide. Now, where does carbon dioxide come from, you might ask? Carbon dioxide comes from the burning of the fossil fuels, and then it gets released into the atmosphere. When carbon dioxide goes into the atmosphere, it will start trapping the heat from the sun, causing the temperatures to skyrocket. So there are methods now to try to remove the carbon dioxide from the atmosphere to try to drive down the rise in global temperatures. Now, this gives rise to what we call the greenhouse effect, which is a natural process by which greenhouse gases like carbon dioxide they trap the energy and heat the Earth's atmosphere, which again gives rise to global warming. So the main greenhouse gas that you know makes the temperature increase is carbon dioxide. So enormous amounts of carbon dioxide have been released into the atmosphere since the 1800s. Now this causes an enhanced greenhouse effect. As you can see in this graph, the Earth has been getting warmer and warmer since the 1890s. The trajectory is that it is increasing dramatically. The warmest 10 years on record occurred between 2000 and 2012, right here, and there is also a big increase. And again, the climate is changing because of these warming temperatures. Based on the increase in global temperatures, ice sheets have been shrinking. The glaciers are melting, so the glaciers are disappearing. When that happens, sea levels begin to rise. When sea level rises, This is going to cause major problems. Many cities are predicted to be underwater in the next few years. Now, there is no credible peer reviewed data to show that climate change is not due to global warming. So, there's definitely a connection, and that's why we need to do something about it. Now, atmospheric carbon dioxide levels reached 400 parts per million in 2013, which is a lot. Now, 300 parts per million was first exceeded in the 1950s, and before this time, levels near never exceeded 300 parts per million. As you can see, it goes up and down, it fluctuates up and down. But now 400 parts per million was reached more quickly than scientists expected, which is very concerning, and that's why we need to look into it. Now, can the effects of climate change be reversed? That was the question posed in the textbook. And the real answer is that this is not easily. You cannot easily reverse it. And that's why it's concerning. And the world, we need to do something. So, even if carbon dioxide emissions are drastically reduced, climate change will continue for hundreds or thousands of years. Now, the other gases that contribute to climate change: CH4, methane, CO, carbon monoxide, which is deadly to humans, and N2O, dinitrogen monoxide. Now, meeting new environmental standards. Now, we need to be shifting away from fossil fuels, but that will require overcoming many, many challenges. We have overcome issues like horse dung, seat belt laws, gas guzzling cars, and low fuel economy, oil embargoes, increasing gas prices, which leads to that picture where a gas in a gas station they write sorry, no gas. So these are all issues that we have overcome, and we need to look into more ways in which we can help the environment. So in 1975, cafe the corporate average fuel economy laws were passed that required increases in fuel efficiency for cars. And by 2025, which is by this year, fuel efficiency must be 54.5 mpgs. So as you can look here, the average mpg is around maybe between 10 and 15 in 1975, but by 2010 both cars and trucks, it's on the increase. So this is something that is promising. In the nature box section in our textbook, the ice core measurements, they mentioned that much of the evidence for climate change comes from measurements of carbon dioxide levels. Now, if we look at the ice core samples can provide information about carbon dioxide levels dating back 400,000 years ago. And bubbles trapped in the ice provide details about atmospheric composition. So the ice core is something that's important, and scientists use it to measure carbon dioxide, and this tells us if carbon dioxide is increasing, decreasing, or remaining the same. But obviously, it is increasing. And the island of uh, Utsira in Norway uses wind energy for power. So this is now we're talking about storing energy in hydrogen molecules, and this island is doing something of that. Now, unused wind power gets converted to electrical energy, which is used to electrolyze water. Again, electrolyze as a verb comes from the process that's known as electrolysis. This is the process of breaking down water. We use energy to break down water to form hydrogen and oxygen gas. Now, when hydrogen reacts with oxygen in a fuel cell, energy is produced. So we are harnessing this energy and convert it to hydrogen so we can eventually create a hydrogen fuel cell. Now, a fuel cell is a type of electrochemical cell, which the definition of it is that a device that can produce power from certain chemical reactions. So in a fuel cell, two reactions are occurring at the same time. One reaction, the electrons are being produced, and the other reaction, the electrons are being used. So it's an oxidation reduction reaction. These reactions are also called as half reactions because they must be paired. And again, these are the oxidation reduction half reactions. So one of the half reactions, as we said, is called an oxidation. And you can see the electrons are produced. The electrons are on the product side. This is hydrogen turning into the hydrogen ion plus two electrons. The other half reaction is called reduction. This is where oxygen reacts with four H plus ions and also four electrons. So as you can see, the electrons are on the reactant side, and we make water as a byproduct. Now, redox reactions combine oxidation and reduction half reactions. And once the two reactions are combined, you can write the overall reaction. In a hydrogen fuel cell or in a fuel cell, hydrogen gas enters the cell and is oxidized at the anode. So in oxidation, the electrons are lost and they travel and go to the cathode. So electrons produced in the reaction leave as electric current, providing electricity. Now electrons return to the fuel cell at the cathode where reduction takes place. So in reduction, the electrons are gained and water is a byproduct. And the last thing for this section 12.5 is that fuel cells are limited by the availability of hydrogen gas. Hydrogen gas is actually rare in nature and is hard to make or store. So the one workaround is if you use electrolysis, you can make hydrogen gas, but it requires a huge amount of electricity. So as you can see in the picture, it says my hydrogen fuel cell car does not make any pollution. Yes, but it uses a lot of energy. And the next section, energy from the sun, which is also an alternative fuel source that we should be thinking about. Most of the world's energy comes from fossil fuels. It is estimated that fossil fuels reserves will last for another 75 to 500 years. So what do we do after that? So we can think about that. We can turn to the sun. The sun provides a limitless source of energy. Plants use the sun for photosynthesis, and we can, try to mimic what the plants are doing. So the plants use photosynthesis to make sugar, glucose, which they use, which is important for them to power the plant. Now, there's something similar that's called a photovoltaic cells. They convert sunlight into electrical energy. Photovoltaic cells are made of sheets of silicon. Some valence electrons in the network of silicon atoms move across a gap from lower energy to higher energy. This movement, this jumping, creates energy. So, sunlight provides the needed energy for the electrons to make this jump. And when they jump, energy is produced. Moving electrons constitute an electric current. So, anytime the electrons move, you're going to get a current which gives rise to electricity. Silicon is a metalloid, and in particular, it's a semiconductor because it conducts electricity only under specific conditions. Photovoltaic cells contain an anti reflective coating, a grid of electrical wires, and a crystalline silicon. Light striking the silicon causes electrons to flow and produce electrical current. And this now let's talk about rechargeable batteries. Now, rechargeable batteries are special because they are electrochemical cells that can be used to store solar energy. Now, a battery is an electrochemical cell but that produces electricity. And a battery is based on two half reactions. And as you can see, the half reactions are right here. It looks very similar to the hydrogen fuel cell. Water turns into hydroxide, and in this case, the nickel turns in 2 plus turns into nickel 3 plus. And this is the nickel MH battery is special because it is rechargeable. You see the double-headed arrow? That means it goes both ways, and that's how you can recharge it. A rechargeable battery uses chemical reactions that are reversible. That's the key word, double headed arrow. They can go in either direction. Rechargeable batteries are a good choice for use in electric cars. Electrical energy flows into the battery to charge it. When the battery is fully charged, the car can be taken for a spin. Now, rechargeable batteries are also used in solar homes to store electricity. So, sunlight comes in and it is stored in the grid, and it could be used throughout the house to power so many things. And you need an electric panel and meter. You got the photovoltaic PV array, the charge controller, and the batteries right here. So, it's very important and a very elaborate setup, but it stores a lot of energy. Now, let's talk about solar energy. Solar energy from the sun can be used anywhere the sun shines. And as you can see in the US, this is the peak sun hours uh, for many of these states. Southern states have more, you can see red, more sun time, which is very beneficial if you want to harness the energy from the sun. If you look at Africa, it's red, a lot of sun there. This desert, the desert southwest and Hawaii receive the most solar energy per day. A lot of sun there. Now, the use of solar energy has been criticized due to the inefficiency of solar panels, which is about 20%. But researchers aim to increase the efficiency. The best experimental panels have efficiencies of 50%, which is better than 20. Now, the green beat section of our textbook has the section energy used by internet server farms. Now, what do we mean by that? So, before the year 2020, half the Earth's population will be internet users. That's a lot. And the data for these internet users is kept in servers farms, also called data centers. And servers use a lot of energy and produce a lot of heat, which is a big problem. So as you can see, the internet users are increasing and the global population is also increasing, but it's catching up. So you got more and more internet users, and a lot more heat is being generated. So every time we use technology, it will actually generate a lot of heat, which is bad for the environment. So these server farms contain many backup servers so that the server farm will not crash. Most servers spend a large amount of time idle but still consume energy. Servers farms produce a large quantity of carbon dioxide, and as you can see, that is their location across the United States. These server farms. Thank you for listening to the lesson. This is chapter number 12. Your next steps is to complete the quiz posted on Bright Space. Email me if you have any questions. Thank you and see you soon.